Hello everyone, today I'm excited to present my ABC Bank credit card approval machine learning project. This project is our module 2 assignment and it focuses on two critical components of ML, workflow, data preparation, and the feature engineering. Our objective is to build a classification model that can automatically predict whether a credit card application should be approved or rejected. Throughout this presentation, I will demonstrate how pre-processing and feature engineering directly impact model performance. Let's get started. First, let me introduce the business context. ABC Bank currently relies on a completely manual credit card approval process. This creates several challenges. The process is very time-consuming and requires significant human resources. Manual review is also prone to human bias and inconsistent decision, making the same application might receive different outcomes from different reviewers, and finally, the inefficiency negatively impacts customer experience. Our solution is to build an ultimate machine learning classification model. This model will make consensus data-driven decisions, reduce human bias, and ultimately improve both efficiency and customer satisfaction. However, we must ensure the model is fair, interpretable, and compliant with financial industry regulation. So let's look at our dataset. We are working with approximate 16,000 credit card application records. The dataset contains 16 features covering various aspects of application information. This is a binary classification problem. We need to predict, approve, or reject. These features fall into four main categories: personal information such as gender, age, and family status; financial data including income type, employment type; asset ownership, like whether the applicant owns a car or property; and finally, conduct information details. The combination of these features will help our model make accurate predictions. Before building our model, we performed explanatory data analysis. During EDA, we discovered several key issues that needed addressing. First, missing values. Several features in the dataset contained missing data that require imputation. Second, we have five categorical variables that need encoding: income type, education type, finally status, housing type, and occupation type. These text-based features must be covered to numbers for the model to process. Third, some numerical features should right score distributions, which could negatively affect model performance. And fourth, we observed potential class imbalance between approved and rejected application. This finding directly shaped our pre-processing strategy. Based on our EDA finding, we implicated three essential pre-processing steps. Step 1, missing value treatment. We identified which columns contain an A value and applied appropriate imputation strategy to ensure data completeness. Step 2, categorical variable encoding. This is a critical step. We use label encoding to transform those five category features. Label encoding works by carrying text categoricals into numerical values. For example, it might carry high, medium, low into 0, 1, 2. This conversation is necessary because machine learning model can only work with the numerical data. Step 3, skewness correction. We adjust the right score distributions in our numerical feature to make them closer to normal distribution, which typically improve the model performance and the stability. These three steps consist our fundamental pre-processing pipeline and ensure our data is clean and ready for modeling. In the encoding phase, we actually conduct a comparative experiment to evaluate different encoding strategies. This is one of our key contributions. On the left side, we have label encoding. This advantage includes simplicity, efficiency, and no increase in dimensionality. However, it has an important limitation. It may introduce false ordinal assumptions. For instance, if we encode application type as 0123, the model might mistakenly interpret this as having an ordered relationship when they are actually just different categories. On the right side is binary or one-hot encoding. This approach avoids ordinal assumptions, making it more appropriate for nominal categorical variables. It also works practically well with tree-based model. The trade-off is that the significantly increased feature dimensionality. So moving to feature engineering, our first technique is PCA. So what is PCA? PCA is a dimensionality reduction technique that transforms our original features into a smaller set of principal components. Each principal component is a linear combination of the original features, and they are ordered by the amount of variance they explain. Essentially, PCA helps us identify the most important pattern in our data. So why use PCA? First, it reduces computational complexity. Fewer features means faster training. Second, it eliminates multicollinearity, which is when features are highly correlate with other. Third, it helps prevent overfitting by reducing the model complexity. And fourth, it significantly speeds up training time. However, there's an important trade-off here. By using PCA, we sacrifice interpretability. The transformed principal components are difficult to explain to business, so you can't easily say principal component one represent income level. In the financial industry, this is particularly challenging because we need to able to explain why we reject an application for regulatory compliance. So we must balance the performance with benefit against the interpretability requirements. So our second feature engineering technique is k-mean clustering. The methodology is straightforward. We use the k-means to group similar customers into different clusters based on their characteristics. We then add them cluster labels as new features to our model. So the purpose is to capture hidden patterns in the data. So customer might be similar overall, even though the individual features differ. Clustering can remove these customer segments. The benefits include reviewing meaningful customer segments, creating groups that might not be obvious from individual features. So now let's discuss our model selection strategy. We test three different approaches to ensure comprehensive evaluation. First, logistic regression serves as our baseline model. We chose it because it's simple, highly interpretable, and trained quickly. Second, random forest. This model handles nonlinear relationships well and can capture complex intersection between features. It also provides feature importance analysis, telling us which variables are most predictive. Third, H2O AutoML. This is an automated machine learning tool that represents a model approach. AutoML automatically test multiple, including GLM, grand boosting, machine deep learning, and stacked ensembles. This performs hyperparameter tuning and provides our with the leaderboard showing which model performs best. So when evaluating our model, we focus on these several keys. We can see the accuracy, AUC, precision, recall, and the F1 score. So we got two questions. So first one, our experiment. I can identify several clean impacts. First, encoding strategy significantly affect accuracy. Our comparison showed a measurable difference in the performance based on how we handle critical variables. Second, PCA reduced training time, right? And this shows the reducing dimensionality doesn't necessarily hurt results. And question 2, what are the stress and the limitation of this technique? In terms of stress, label encoding is computationally efficient and doesn't increase that PCA dramatically speed up training and removes the k-means rebels customer segments that provides additional predictive power. So the core trade-off is between performance improvement and the model expandability. In the financial sector, this balance is especially critical due to regulation requirements. So the question 3, I can see 3 main directions for improvement. Yeah, we got the first, collect more features, address class imbalance with smooth, and create domain specific features.